Good morning, everyone. Thank you for joining us on this webinar on RTDs, thermocouples, and thermistors. We'll go into the recording straight away, but if you do have any questions, feel free to put them in. We'll get them at the end.
Hello and welcome to today's webinar. In this webinar, we will look at how to apply RTDs, thermocouples, and thermistors to your Horner controller. These are the three most popular temperature sensors for industrial applications, and in this webinar, we are going to explain how they work, discuss how best to apply them, and go through some great tips on how to apply them. There will be demonstrations throughout, and we will finish with a Q&A session. Let's begin with a classic, thermocouples. Thermocouples have been around for a long time. They are relatively inexpensive, with the widest temperature range and fast response times. However, they have some disadvantages too. They are a little tricky to work with, and they are susceptible to electrical noise, as the signal they generate is quite small. Where are they used? Any application measuring high temperatures and requiring fast response times is ideal for thermocouple use. Some examples include injection molding, packaging, industrial furnaces, kilns, and gas turbines. How do they work? Thermocouples generate a tiny voltage when two metals are joined at a tip. Thermocouples are named by type, each a unique combination of metals. Different metals and different pairs of metals will generate different voltage curves. Here we can see a graph comparing some of the most common thermocouple types. There are a wide range of values, and each thermocouple is ideal for a different application. As mentioned earlier, different combinations of metals create different types of thermocouples. This table shows some of the most common types on the market today. This also shows some of their extension grades, which we will discuss more momentarily. Of these types, K, J, and T are the most popular in industry today. Type K is popular for high temperature applications, Type T is popular for cold or low temperature applications, and Type J is popular for general purpose applications. When installing a thermocouple to a measuring instrument, we have to be careful as this will generate a tiny voltage due to the thermocouple effect. This is what we call a cold junction error. Any measuring equipment that connects to a thermocouple has to take into account the cold junction compensation. To eliminate errors at the measuring junction, the temperature at the cold junction is measured, and the expected loss is subtracted. Next, let's discuss color convention. As the types table revealed earlier, there are many different color codes that you will encounter when dealing with thermocouples. However, one that is universal to all thermocouples is red. The negative wires are always red on any thermocouple you might use. Positive wire colors vary by type. For instance, it's yellow for type K thermocouples. How do we install a thermocouple? Installing a thermocouple will be different for each system, but we have some general tips to remember that apply to most cases. First, we must ensure that the wiring used to connect the thermocouple to the measuring instrument matches the thermocouple type of the sensor. This is critical as otherwise there will be cold junction errors along the length of the connection. Next, be sure to avoid temperature gradients along that wiring. This will also throw off our readings. Finally, pay attention to grounded versus ungrounded sensors. What are grounded and ungrounded sensors? If the hot junction of the thermocouple is electrically conductive with the sheath that it's installed in, that is what we call a grounded thermocouple. This is useful for several applications, but not all I/O modules will work with this kind of thermocouple. Be sure to check what your I/O modules can support before installing any thermocouples. Of course, we can connect our thermocouples to the Horner OCS-I system. Whether it's one of our all-in-one controllers or a modular controller, Horner controllers include support for thermocouples. We recommend the ADU100 Universal Analog Input Module from the modular controller range. It can handle 16-bit 4 to 20 mA, 16-bit 0 to 10 volt, and also direct conversion of thermocouple and RTD readings. With Horner OCS-I, there are 3 connection terminals for each channel, and in this case, the negative leads connect to the A input and the positive leads to the B input. Grounded thermocouples are also supported. Now, let's move on to the next sensor in today's webinar, RTDs, or resistance temperature detectors. RTDs are accurate and quite easy to work with, especially when compared to thermocouples. However, they can sometimes be expensive, and they can't be used over 850 degrees Celsius. Any application where precision and stability are critical is ideal for RTDs. For example, food and beverage, pharmaceutical, and power generation are all great applications. How do RTDs work? As the name implies, when it is exposed to different temperatures, it will have a predictable resistance value. RTDs are named both for their material and their resistance at 0 degrees Celsius. The most common RTD by far is Platinum 100 or PT100, which is made from platinum and has a resistance of 100 at 0 degrees Celsius. Here we can see resistance versus temperature of a PT100 RTD. We can see it's a fairly linear relationship between them. This is another reason they're so much easier to work with when compared to thermocouples. Just like thermocouples, there is another issue we need to watch out for when installing an RTD into the system. If there is enough resistance in the wiring between the RTD and the measuring device, the results can be skewed. To compensate for this extra resistance, we use something called 3-wire, or sometimes 4-wire, RTDs. Most industrial RTDs are 3-wire RTDs, which means they have an extra wire on one side of the sensor that is used to send out a tiny current. This small current is used to measure the resistance of the lead wire. The current must be small, otherwise there is a risk of the RTD sensor self-heating. Next, let's look at color conventions. Unlike thermocouples, there is very little universality to the color conventions on RTDs. However, most popular RTD manufacturers follow these rules. Red wires are for excitation, or carrying the current to the sensor, and white wires are for measurement, or measuring the voltage drop across the sensor. When installing an RTD, we should ensure that we are using a 3-wire or 4-wire RTD. We also want to keep the extension wire resistance to less than 10 ohms. Belden 8770, for example, is a good choice of wiring. And finally, if we have a shielded cable, we need to make sure to earth it, and if possible, away from the transmitter or PLC. How are RTDs connected to the Horner OCS-I? Most RTDs will have 3 leads. The 2 red excitation leads connect to A and B, and the white measuring cable connects to C. As before, we recommend the Horner ADU100 Universal Analog Input Module. Now, let's look at the final sensor of today's webinar, thermistors. Thermistors are extremely simple to use and are quite inexpensive. But this comes with several disadvantages. They can only measure ambient type temperatures, their ability to resolve different temperatures varies depending on the temperature, and they're not always highly accurate. Where are they used? Due to some of the disadvantages we just discussed, thermistors are not a popular choice for most industrial uses. However, any application with an environmental temperature range, and where cost is important, they are likely to be used. For example, HVAC systems, household appliances, and even some automotives all use thermistors. How do they work? Like RTDs, thermistor resistance varies with temperature. However, thermistor resistance values are much higher, typically 10,000 ohms at 25 degrees Celsius. This graph shows a 10K NTC thermistor, which is the most common industrial thermistor used today. We can see a very limited temperature range. Even at 0 degrees Celsius, we can see it's around 30,000 ohms. The most common thermistors are 10K type 3 and 10K type 2. Like RTDs, do we need to use lead wire compensation? No, because the resistance of the sensor is so high, lead wire resistance is not relevant, so special compensation is not needed. When it comes to color conventions, thermistors have no polarity. so they can be connected either way. And beyond polarity, there's very little strict color convention between thermistor types. Sometimes type 3s are gray and type 2s are green, but this is not universal. When it comes to installing thermistors, make sure the thermistor type matches the measuring instrument. Otherwise, just make sure it's only dealing with ambient type temperature ranges. And we don't need to worry about polarity, so connecting the wires in either way will not cause issues. Because the temperature range is so large with thermistors, we have created a dedicated module exclusively for them. The NTSC 800 thermistor input has 8 channels of input. This is a new module dedicated entirely to thermistors. And that concludes our overview presentation of thermocouples, RTDs, and thermistors. Now, we are going to show you how to install these to your Horner OCS-I device. Here we are on the bench. For this demonstration, we have set up a CPU 300 with two OCS-I modules, the ADU 100 Universal Analog Input and the new NTC 800 Thermistor Input. We also have a HMI touchscreen connected directly to the CPU 300, which isn't strictly necessary. The CPU 300 has a screen of its own and can handle all the logic and control of a system without any need for a separate HMI. However, for the sake of this demonstration, we are going to take advantage of the HMI touchscreen for a more visually appealing graphical interface with touchscreen capabilities. Let's switch to Cscape and take a look at the logic. To start, we will navigate to hardware configuration. Here we can see our CPU 300 correctly registered. If we click on the local I/O tab, we can see the analog input module and thermistor input module. Let's first look at the analog input module. This is a 4-channel module with the capability to filter data if necessary. With each channel, we have access to a long list of data types: 0 to 10 volts, 0 to 20 milliamps, 0 to 60 millivolts, loads of thermocouple types, and some RTD types as well. For this demonstration, however, we are using type K thermocouples, and that will be reading in degrees Fahrenheit. On channel 2, we have a PT100 RTD, again reading in degrees Fahrenheit, and we have disabled the last 2 unused channels. That's the configuration for our analog input module complete. Next, let's look at the thermistor input module. This is an 8-channel input module with the capability to filter data as well. This is a new module, so currently the only supported data type is the 10K thermistor type 3. So we will select that, and once again we are measuring in degrees Fahrenheit. The other channels are all disabled as they are not in use for this demonstration. Now let's examine this at runtime. Here we are on the bench. On our HMI touchscreen, we can see the thermocouple reading, which is connected to the first 2 slots here. If we heat up our sensor, we can see the reading increase. We also have an RTD sensor connected to the same module, and as we can see, it is measuring the ambient temperature of the room. Finally, we can switch to our thermistor, and once again we can see an accurate reading displayed on our HMI touchscreen. It's as simple as that to connect RTDs, thermocouples, or even thermistors to any Horner OCS-I. And that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, nice and short one this morning. I don't see any questions in on that as yet. As usual, if we have the list of the upcoming webinars either through the newsletters or on the webinar section of the website. So if you see anything that you like, feel free to register and join us on a Thursday morning again. Other than that, I think we can leave it there for today. Thank you all for joining, and we'll see you next time.